We're looking at an exploration of the quantum prisoner's dilemma. To start, we're going to review the classical version of this game. Let's say we have Alice and Bob. Both are accused of committing some crime together, but there's not enough evidence to put them both away. So, they're given the option to stay silent or rat out the other. If they both stay silent, they're given 1 year in prison each. If Alice rats out Bob, Bob gets 5 years while Alice is free, and vice versa. If they both rat each other out, they both receive 3 years in prison. We can visualize this on a chart. Rationally, the best decision for both of them is to rat the other one out, or defect, but that leads to a worse outcome. Instead, mutual cooperation is the best option. This makes the game paradoxical. Now, what if we added quantum rules? This time, let's give each prisoner a qubit. It's given in the initial state of C. Then, these qubits are passed through an entanglement operator J, and through this, they become linked in a way that isn't possible in classical game theory. Mathematically, this is how J is defined, where gamma is the entanglement parameter. If it's equal to 0, the game is classical. The higher this value, the more entangled the game is. D is the classical defect move, and the tensor product means that the operation is acted upon both qubits. Let's talk more about J, specifically what restrictions are placed on it to allow fair interactions. First, J needs to be unitary. Here's a mathematical condition, where J dagger is the Hermitian transpose. Quantum mechanics requires that probabilities sum to 1. So, if J weren't unitary, we would receive a physically impossible measurement. Second, J needs to commute with each classical move. Commutation means that two operations can be placed in any order and you can still get the same result. This makes sure that our classical moves are still playable in this framework. And finally, J needs to be symmetric, in order for the game not to favor one player over the other. Back to the game. After the J operator has been applied, Alice and Bob can now apply a unitary transformation to their qubits, instead of just choosing C or D. This gives them both a number of different quantum strategies to choose from, like mixed states, for instance. We can call this the Q move. And, to finish it off, J dagger is applied to reverse the entanglement, making sure we could actually measure the final result. Here's an example chart of some of the payoffs possible with the quantum prisoner's dilemma. Depending on what our entanglement strength is, the quantum move allows for better outcomes, removing the defect trap, and achieving a better cooperative outcome. Now, with that 3-minute preamble out of the way, what are we trying to do? Well, you remember how we had a symmetry restriction on J? Well, fuck you, we're entirely removing that. We've been exploring an asymmetric version of this game, with a generalized J. Instead of using the standard entanglement operator, where both players experience the same entanglement transformation, we generalize to this form. This means Alice and Bob are no longer entangled in the same way. Since A and B are now different quantum operations, we want to see what happens when one player is, potentially, more strongly entangled than the other. To ensure this new version is well defined, A and B must satisfy two conditions. First, A must be either Hermitian or skew Hermitian. The operator J is defined using matrix exponentiation, I said that correctly, which can only produce unitary transformations when the exponent is one of the two. Second, A must commute with D. This means that A and D can act in any order without changing the result. If A commutes with D, then it must commute with J, since J commutes with all possible strategy choices. In short, we are looking to see if we could give one player an unfair advantage and exploit the other player. Kinda fucked up, but it's fun and interesting work, so it's fine.